Hello folks, we're here for another video tutorial. I'm sorry for the delay between the last video and this one, but I hope that from now on I will be more available to record some videos about Ansys and other types of simulations. So today we will be looking at a very simple structure that was actually designed in Inventor and then imported into Ansys. And the structure comprehends two end plates, two plates actually, and a beam. The beam is welded to this plate, and then we have 6 bolts securing the connection to the other plate. Actually, this plate can be representing a lot of different things. Actually, I didn't design a column because it would require much more type of, um, of processing and the visual effects, and actually what I was looking for by recording this video can be achieved in this way as well. So with no further delays, let's go into the analysis. So before looking at the results, we have to understand what is beyond this analysis. So I've settled a lot of different connections. All of them are from one of 3 types. They can be either frictional or frictionless or even bonded. Well, of course, that each type of connection is applied depending on the body and on the part of the structure that we are looking at. So, for example, this frictional contact is presented between the 2 plates. So actually the 2 plates can slide from each other. That's why they can separate from each other as well. We also have frictionless contacts between the bolts and the plates. Then I have a bonded contact between the beam and the plate, which is trying to simulate a welding beam. Once again, I have bonded contacts between the nuts and the bolts. All right, so now, looking at the contact tool, we see that there aren't any errors, so we have all good to run the analysis. But before, we also have to look at the mesh. And the mesh is not perfect, but it's fine. The model can run with this type of mesh. Actually, I've only performed 2 changes on the standard mesh, and I've settled the relevant center to medium instead of coarse as normally is the default the default definition on the program. I've applied a face sizing of 15 millimeters on this on this size of the plate, and the body sizing of 4 millimeters on the bolt. So that's all it. I've just done this in mesh, and then I've jumped to the analysis itself. So the analysis is made of 2 steps. The first step is where we run the pretension, and the second step is where we apply the force. Actually, I've applied 6 bolt pretensions, but in a further analysis, I suppressed the pretensions just for experimental purposes. But actually, I've applied a preload of 15 kilonewtons on each bolt. And I also applied the fixed support on the lateral faces of this plate. So now, what is the big difference between this analysis and other analysis? Well, the big difference relies here on a remote displacement instead of a force. Why? Because I'm not applying a force on the structure, I'm applying a displacement. And the purpose of the analysis is to analyze the force reaction. So I will be looking at the force reactions on the fixed supports. So instead of applying a force and searching for a displacement, I'm applying a displacement and searching for a force. Okay? So that's the reverse mechanism, but it works perfectly. In some cases, it works even better than applying force, especially if you're looking for an experimental and numerical comparison. It's not my case, but it would work for that as well. All right, so now looking at the solution, we can see that I have a 15 millimeter displacement, um, which was the displacement I applied. I also have the equivalent stress, and the maximum equivalent stress is 700 megapascal. Well, I didn't mention before, but the material that is applied on the structure is the nonlinear steel uh, that Ansys presents us. Is actually the standard nonlinear steel. So it's a bilinear model, and I think that the yield stress I'm sure that the yield stress is much lower than this, and even the ultimate stress is much lower than this. So here in the bolt wouldn't resist and would collapse, all right? So it would fracture here, and this would not resist. However, on other parts of the structure, I have very uniform stresses. I have stresses ranging from 150 to almost 400 megapascal. Even on the nut, I have 400 and well, almost 500 megapascal. So even the nut would failure, um, but uh, everything looks fine. And then I can actually look for the force reaction, and I can see that for pulling the beam 50 millimeters, it would be required a 600 kilonewton force. So that's a very big force, actually a huge one for the structure, and that's the reason why um, this this structure wouldn't resist to that type of efforts. Well, actually, after looking at these results, I made a few graphs, and you can see a clear linear zone here and here. Actually, these graphs have a preload, um, but I have different preloads here, and you can see that it doesn't change that much. So it's basically the same. I have a linear region here and a nonlinear region over there. You can see that I reach the furthest actual the biggest displacement when I apply 600 um, 600 force, 600 kilonewton force, and it's clearly visible the differences between the linear zone and the non-linear one. Well, actually, I was pretty happy with this analysis. It's a very simple one. You can perform this yourself, study your model, dedicate some time to analyze what is going not as good as you expected it before, but try to analyze, try to look into those problems and create your own models. Try to simulate your own structures, um, and it doesn't matter how complex they are because you can start from a very basic one and then step after step complicating the model. All right, so I hope you enjoyed it. In the future, we will be looking for another type of analysis. I'm hoping that in the near future, we will be looking for an explicit dynamics one where I will be analyzing the cracking and the failure of the bolts, which is a very interesting thing to do. All right, so stay tuned for more updates. I hope you have enjoyed it. Give a thumbs up and comment on the comment box below. Thank you very much for your time.